Hello, everyone. This is Mr. Neighbor, and we're talking about the last section of Chapter 15, which is wave interactions. The very first part about wave interactions is wave interference. When two waves combine, so you have one wave traveling this way, another wave traveling that way, what happens when they interfere with each other? So there is constructive and destructive interference. Constructive interference is when two waves are on like the same side and they add to each other. Destructive interference is when they're on opposite sides and they subtract from each other. So the formal definition of constructive interference is it occurs when the crest of one wave overlaps with the crest of another wave to create a wave larger than either. So if we look at that, we have one wave that is one tall, another wave that is one tall. So when they are completely overlapped, they are going to be a wave that is two tall. Same thing right here. This is another example where we have one below, another below, and when they combine, they will have amplitude that is two below. These are just added together. So this height plus that height again, which would put it right here. So it's a lot of kind of looking at certain spots and creating dots to kind of find that wave. When we have destructive interference, that means those overlapping parts are going to go against each other. So let's look at that. So if this one is one tall and this is negative one tall, when they combine, they're going to cancel out to be zero. Here we have positive a half. Here we have negative a half. When they combine, it's going to be zero. Same thing all the way across, so you get this flat line. The waves cancel out. So if this was a sound wave, at that point, you would hear no sound. So this relates very, very much so to acoustics. And actually, it relates to light a lot too. Let's do a practice problem. Here we have one wave and another wave, and we're going to combine them. So let's look at different points in this wave. So here I am at 0, and here I am at 0. So the start of this is going to be at 0 as well. The next most obvious point is probably the first crest. This one is 2 tall. This one is 1 tall. So when I combine those, that will be 3 tall. So that looks like it happens 2 blocks over. So 2 blocks over, it's going to be up here. Next, at 4 blocks over, it looks like both are at 0. So I will add 2 zeros together and get 0 out again. Here I have a trough that is 2 below. Here I have another trough that is only 1 below. So at this trough, when they are combined, I will have a trough 3 below. And then continue doing that. Here we have another point where they are both at 0. So that's 2 more away. And it looks like that constructive interference is going to continue and have another crest and then end over here. And then we can just combine these in a fluid motion. We could add a couple more dots to see the specifics of it, but it's going to just create a nice sinusoidal wave, kind of like a sine function in math or a cosine function in math, just a bigger amplitude. So that is the combined wave when the two waves interfere. Let's look at another example. So here, it looks like both start at 0. So let me mark that. Next point would be the crest here, which is 2 above, with the crest here, which is 1 below. So when I combine those, it's going to only have a crest of 1 tall. So right here. Then it looks like they match up again where they're both at 0. Then we have a trough of -2 and a crest of 1, which would make a total of -1 for the combined. Then it looks like they both hit 0. And then we have another 2 crest and -1 trough. Put that there. And then it looks like both are 0 again. So here is the new wave pattern. Again, looks like a sinusoidal wave. Not all waves will look at this. Sometimes we'll do examples where the waves look very boxy and they're like this. instead of these nice sine cosine graph type waves. So you might have something that's more boxy, and really that's only for graphing and practicing purposes. The waves will look like this truly, but sometimes for graphing purposes we do them like this to help practice. All right, so we need to keep in mind this wave interference that we have happening. When you vibrate a string, or anything, it could be air too. I'm going to focus on a string right now. When you vibrate that string, you're sending one wave out, it is hitting where it's connected, and it's sending another wave back. When those waves interfere, sometimes they cancel out, sometimes they add together. Sometimes it looks very, very funky. But when it turns out to look very, very clean, is when you have a standing wave. So a standing wave, your vibration will be happening when we're talking about a string so fast to the point where it looks like you have this kind of eye-like shape, this slit, and it stands there. It looks like it's not moving, hence the standing wave. It makes it stationary. When you increase the frequency, so moving the wave faster, once you hit a certain frequency, it will turn into two slits. Before that, it won't look like a standing wave. It'll look blurry. But as soon as you get to a certain frequency, it will become two slits. And then up the frequency again, vibrate faster, then you'll get three slits. And you can have as many slits as you want. These are eventually going to be called harmonics, which we'll talk in the next section, which relates to how we hear sound, how we hear music, and how those are different from one another. So the parts of standing waves that you need to know. First, the antinode. The antinode is the point of the wave that moves the most. It's the top and bottom, the big part of the slit. The node are the points that appear that do not move, as if they're completely stationary, where the two waves are canceling each other out, or the waves are just, the wavelengths always match up there. So the nodes happen at the two ends on, say, a string instrument, because it's connected at the top and at the bottom. And then as you increase the frequency, nodes will appear in the middle, and they'll always be halfway in between, breaking up the antinodes equally. So we're not going to do much with this now. It makes more sense when we talk about music and harmonics in the next section. So just know the different parts. Node, there's always one more node than an antinode. Antinode is the big part in the middle. That's the movement part. That looks like it's now standing still, hence the standing wave. Lastly, I want to just speak briefly on resonance. Resonance is the point where the vibrations through an object matches the natural vibrations of that object. Okay, things, materials, substances have a certain natural vibration, a frequency that they attune to. So even though the object may not be vibrating, there's a frequency that forces it to vibrate because it matches the object's natural frequency. So for example, an opera singer hitting a note and shattering a crystal glass is because its crystals have a natural frequency that the opera singer just hit. So they begin to vibrate, and when glass vibrates, it's going to break and shatter. You will notice this a little bit more when we talk about guitar, when I'll bring it up in class. When you hit a resonant point, you will see the string vibrate. But if you don't hit a resonant point, then it won't vibrate. But that deals with harmonics. So the harmonics are the things that are making the resonance happen. So it's the natural tendency for an object to vibrate, and we're attuning to that, making the resonance. And maybe to help this sink in a little bit more, think about the word resonate. When something resonates with you, it stirs you deep within. You have a connection to it. That's what resonance is. It's a connection between something to another, specifically the vibration to an object, its natural vibration.